All right, in this explainer, we're going to dive into a topic that might just turn your understanding of physics completely upside down. It's this idea that the particle, the fundamental building block of our universe, might be nothing more than a convenient illusion.
Okay, let's really dig into this, because this one single question is the absolute core of our whole explainer. What if everything we thought was a tiny, solid thing is actually just a persistent ripple in a much deeper, more fundamental ocean of fields? To even get there, we first have to take apart something that, well, we all learned in school, that neat and tidy picture of how the universe is organized.
So, you know how physics textbooks draw a really clear line in the sand, right? On one side, you have the real stuff, fundamental particles like electrons and photons. And on the other side, you've got quasiparticles, things like phonons, which are basically just vibrations in a crystal. We're always told these are just useful fictions, clever mathematical tricks to make our lives easier. Well, according to a framework called deterministic field realism, this whole way of thinking isn't just a little off, it's completely backwards. The things we've been calling fictions might actually be showing us what's truly real. So what is this new picture of reality? It's actually pretty simple, but it's also incredibly profound. DFR says that fields, and only fields, are the fundamental reality. Everything else, all the things we call particles, from electrons to phonons, they're just stable patterns or configurations within those fields. An electron isn't a thing, it's a stable knot in the electron field. A phonon is a stable ripple in the lattice field. See? Neither one is more real than the other. Now, that's a pretty bold claim, isn't it? So where's the proof? Well, it lies in this really fascinating phenomenon where our so-called fundamental particles can literally just vanish.
Yeah, the best evidence for this whole field's first idea comes from what are known as hybrid quasiparticles. These are brand new entities that form when two different field excitations, say light and vibration, get so tangled up together that neither one can exist by itself anymore. Let's take the phonon polariton, for example. When light in the infrared spectrum, a photon, hits certain crystals, it doesn't just bounce off the lattice vibrations, the phonons. No, it merges with them. And in that very specific region, you can no longer find a pure photon or a pure phonon. The only thing that's there is this new hybrid entity, the polariton. The hybrid becomes the new reality.
And this isn't just some philosophical hand-waving. You can actually measure it. In thousands of experiments, scientists have seen what they call an anti-crossing signature. Think of it like this. If the photon and phonon were just interacting, their energy levels would cross paths like two roads. But instead, they push each other away, creating two completely new energy pathways. This is the smoking gun, the definitive proof that a true merger has happened. And this is not some rare one-off thing. The list of these observed hybrids is long, and it's getting longer all the time. We've got exciton polaritons, magnon polaritons, magnetic polarons, you name it. And every single one is another case where distinct fields merge into a new single reality. This proves it's a fundamental transformation, not just a simple interaction. Okay. So fields are fundamental and they can merge. That's a really cool shift in how we see the universe, but does it actually do anything for us? Oh, absolutely. The practical applications here could be nothing short of revolutionary. Let's just start with this simple question that actually challenges a massive assumption. Why do we power our entire world with electrons flowing through metal wires? The answer has nothing to do with physics. It's just history. It's the first way we figured out how to do it, and we built our whole world around it. But think about it. If energy is just a configuration in a field, there's absolutely no reason we have to stick with the electron field. We could use magnons, which are waves of magnetic spin. We could use phonons, basically sound waves, or we could use any number of other quasiparticles that can carry energy. So let's take magnons. When electrons move through a wire, they bump into stuff, right? They create friction and heat. We call that joule heating, and it's the reason we waste between 8 to 15% of all energy generated just moving it around. But magnons, they carry spin, not charge. And if there's no charge flow, there's no joule heating. And listen, this isn't just theory. Researchers at MIT have already built magnetic circuits that can perform logic operations with no electricity. The result? Get ready for this. A staggering 90% reduction in energy consumption compared to conventional electronics. This could completely change the game for everything, from massive data centers to the computer chip in your pocket.
All right, let's really push this idea now to its most mind-bending conclusion. If quasiparticles are just as real as fundamental particles, could we use them to study some of the biggest mysteries in the universe, like, say, gravity?
You won't believe this, but in March 2024, researchers did exactly that. They observed something they called chiral graviton modes. These are quasiparticles, these collective excitations inside a material that act just like the hypothetical graviton, the particle we think carries the force of gravity. To put it simply, they found a way to create and study an analog for gravity right there in a lab.
And the speed of discovery here is just breathtaking. Hot on the heels of that 2024 observation, theorists in 2025 predicted that graviton polaritons could exist, a hybrid formed by coupling these gravity-like modes to photons. A gravity-light hybrid we could poke and prod in a laboratory. Now this opens up some really wild possibilities. For instance, we know that in superconductors, phonons create an effective attraction that glues repelling electrons together into something called Cooper pairs. So, could a similar trick, using these new gravity-like quasiparticles, create attractive forces strong enough to help us crack nuclear fusion?
Now, let's be realistic for a second. The energy scales here are just worlds apart. The binding energy for Cooper pairs is minuscule compared to the absolutely massive Coulomb barrier for fusion. We're talking about a gap of 8 orders of magnitude. So, while the physics of quasi-particle attraction is proven, closing a gap that huge is a monumental engineering challenge.
So, let's pull all this together. What does this quasi-particle revolution really mean for how we understand reality itself? It's asking us to completely update our mental model. First, fields are what's primary. Second, hybridization isn't some weird exception, it's the default behavior of the universe. Third, the very idea of a fundamental particle depends entirely on the context. An electron in a vacuum is one thing, but inside a superconductor, it basically stops existing, replaced by the Cooper pair. And finally, those huge energy gaps we talked about, they might just be engineering problems, not fundamental laws of physics telling us no. And that really brings us to the final crucial takeaway. This whole zoo of quasiparticles we're discovering isn't some weird footnote to physics. They aren't just emerging from a more fundamental reality of particles. No, they're pulling back the curtain and showing us what reality has been made of all along. A dynamic, interacting, and unified universe of fields.